Yes, so we'll quickly start. Today's session, I'll try to connect the dots between what a RAG is. How many of you know what RAG is? How many of you don't know what a RAG is? Perfect. So after today's session, you will have a clear understanding of what RAGs are, what is GraphRAGs, where is it required, how does Gemini come into the entire picture when you think of GraphRAGs, and finally, we'll also touch upon large language models in general in terms of how they kind of power up everything so that everything works together. Okay, so I'll quickly start. Before we start, today's talk is centered around four major categories or four major subtopics. We'll start off with what large language models are. We'll also go through graphs, given that we are talking about GraphRAGs. Then we'll also look at say typically a RAG workflow in terms of how this entire piece is built, and finally we'll also look at the need for a GraphRAG system. Okay, so that is the agenda that we have. We'll start off with large language models. How many of you have never used a large language model recently? Like anyone in the room who is not using Gemini, ChatGPT or other models for their use cases? Anyone in the room? So in a very short duration of time, right, I'm glad no one raised their hands. In a very short duration of time, everyone's kind of started using LLMs extensively so that everyone can kind of get things done quickly, correct? That is where LLMs come into picture. Now what are large language models? How many of you are college students here? Perfect. How many of you aspire to reach GenAI kind of a role or are targeting GenAI roles or data science roles in general? So quite a lot of you. So typically how a large language model works is it's basically a good, smart next word predictor. That is how a large language model is. So a large language model basically takes in text till a certain point and generates the next token or output. It feeds that in again and then generates responses as you keep moving forward. The process of generating a response or the entire piece of text is what is done sequentially. What you feed in at one go is something that happens parallelly, which is something that was like a big breakthrough in terms of how large language models work. Okay, so typically a large language model, whether you use Gemini, Claude, GPT or any other model, it basically is a very smart next word predictor. That is how a large language model is defined. Now imagine if I have a sentence like this: cat sat on a, based on whatever you input and based on whatever the large language model has basically learned so far, it will generate the next word, which is mat, with a higher probability value. What happens later on is once you have this entire sentence, cat sat on a mat, that will be passed again to the LLM and it will generate the next probable word, which gives it maximum probability. Okay, so this is how a typical large language model works. We use it for generating code, we use it currently for generating emails, and there are a truckload of applications that we've discovered. We've now powered agents using LLMs to kind of carry out various tasks. This is a favorite thing that we do right now. For all the code that we generate today, we extensively use large language models by passing in a prompt, and we expect the entire response to be generated by the LLM. So code completion, generating ideas, if I have to plan for a trip, if I have a project in mind that I have to create a solution for, then essentially what I do is I basically pass that input prompt. The LLMs these days are smart enough to do research as well, go online on web browsers, search the internet, give the right context and generate a response as well. So LLMs from where they were to where they are now, there's been a huge shift in terms of their capabilities that you can kind of think of when you are using a large language model. Now LLMs help us prototype quickly. Imagine if I have to develop a web application. Prior to this entire process of using LLMs, what we used to do is we used to define what our web application should look like, the front end, the back end, join both the interfaces together. There would be a lot of issues while you kind of keep creating the entire solution. All of this has been now given to the LLM to generate different parts of the code, and the LLM will kind of quickly generate those entire code bases for you as well, correct? Now, for all of you who want to start their career in generative AI in general, if there is one research paper that I would urge all of you to read, is this paper open sourced by Google called as Attention is All You Need. Okay, this is one such paper that kind of revolutionized how LLMs work. Before this, what we had were RNNs, LSTMs. This is back in 2016, 2015. Back then, RNNs and LSTMs were used for a lot of NLP applications. But after this paper was adopted, that is where all of the entire changes in the NLP or LLM ecosystem came about. So, if there is one research paper that I would highly encourage all of you to read, then this is the paper that I would encourage all of you to read, which is Attention is All You Need. Again, open sourced by Google. You can go through this as well. This right here that you see, right? It contains two major sections. This is the encoder block of a transformer architecture. This is the decoder block of the transformer architecture. So essentially, what Google was trying to solve for is the translate problem, which is where they kind of came up with this entire architecture. How many of you use Google Translate? So back in 2016-2017, Google had a very simple way of translating text, and text translation was not very accurate, which is where they were working on the translation problem, which is where this entire architecture came into existence. So here, when you think of this entire architecture, there are two blocks. You have the encoder block, you have the decoder block. Both of them are joined together in the original transformer paper. But now when you look at how this entire architecture is used, the models that you use, how many of you use Gemini day to day in your day-to-day task for generating code, etc.? The Gemini models fall into this category, which is the GPT model category or the decoder only model category, where they have only the right hand side section, not the left hand side section. Okay, Google again open sourced a very famous model called as Bhatt, which is encoder only model. Okay, so there is the left hand side that exists, right hand side is not needed for encoder only models. Decoder only models are only the right hand side is required, left hand side is not required. Okay, and then when you combine both the sections together, if you want to perform a language translation task between different languages, then you start going towards the entire full-blown transformer architecture. Okay. This was the first section that I wanted to cover. The second section that I want to cover is around graphs. Okay. Now, what are graphs and why do we require this in case of GraphRAGs is what we'll come to. But think of graphs as basic nodes that are joined together or connected together using a relationship. Okay, so graphs basically join two sets of properties together using a defined relationship between the two set of entities that we are looking at. We'll kind of do a deep dive into this as well. But before we go there, the reason why we are using a graph database for a GraphRAG and not a normal database is what I'll cover today. How many of you know MySQL, SQL language? So SQL is a very old technology. It came into existence in 1980s. Very good with respect to keeping relations. Very good with respect to keeping relationships between different schemas that you have. But there was a problem with MySQL, which is it couldn't scale really well. So imagine if you have 10 billion records and if you have to perform a self-join on self-join, then the amount of time it will take will be really large, right? So as the data sizes kept increasing, the bottlenecks of MySQL database were clearly evident. Okay. Next came something called as NoSQL databases. Have you heard of this database called Cassandra? Elastic is also there. So there are multiple NoSQL databases where there's no relationship that is captured between different schema. You can have a simple JSON-like representation, and the entire good part about a NoSQL database is it scales extremely well, right? You can have billions and billions of records. If you want to filter based on that, you can do a filtering logic based on the data that you have, right? But the problem with NoSQL is you cannot capture the relationship that you could capture using MySQL databases, right? So to counter that, we have something called as graph databases which solve the issues of both MySQL and NoSQL databases. So graph databases capture relationships really well. That is the first point, the advantage of MySQL databases. The second advantage of using NoSQL was it could scale really well. So graph databases can also scale really well. Just a quick show of hands, how many of you use Instagram? Perfect. So if I take a data set of 1 million of all of you here, right? Imagine there are 1 million people in the room, and if I try performing this activity of finding friends of friends of friends of friends of friends, like there are 5 levels of self joins, think of it as 5 levels of self joins. If I have to run this query and get the results of all of the friends of friends of friends of friends of friends for all the individuals that are present in this data set, MySQL would basically not complete in the right amount of time because it is unable to process so much of self joins at one go. Whereas if I want to do this activity using a graph database, it takes around 2 seconds. So this complex query of finding friends of friends of friends of friends of friends, like 5 level depth of self joins that you can think of, if I have to perform this using a graph database, it takes 2 seconds for execution, but on the other hand, your MySQL will not be able to execute this entire query. Okay, so this is the advantage in terms of speed up that we are talking about. Now we'll kind of go in depth in terms of how graphs function, right? This section will be more of like understanding, say English that we had in 8th and 9th, and then kind of tying that back to graph structures, right? What do you see here? Do you see 2 circles and an arrow pointed from one circle to the other? The circles are basically nodes. The arrow is a relationship. This is the fundamental block that you will find in every graph database. So in a graph database, you will have nodes and relationships. Nodes are what you have inside the circles. Relationships are the arrows between nodes that connect each other, right? So this is the initial building block. Now, if I have a sentence and if I have to convert that into a graph database equivalent sentence, then all you have to do is all your nodes or all your nouns in a sentence translate into a node. Okay? Now, if you have this sentence, which actors play in this movie, right? What are the nouns? Are the words that I have highlighted, are they nouns or verbs? Like again, going back to English 8th and 9th. In this sentence, which actors play in this movie? Is movie a noun? Yes, no, yes. Are actors the word, is it a noun? Pronoun etc. is also considered as a noun in this case. But is it a noun or is it a verb? Noun. So all the nouns in a sentence, once you plan to create a graph database or once you translate into a graph database kind of a structure, all your nouns will become a node. All your verbs in the sentence will become relationships between 2 sets of nouns. Okay, I'll quickly go to the next screen so that all of this makes sense. Again, a lot of theory here. But before we move there, is play a noun or a verb? Noun, right? Verb. Is this movie, when you direct a movie, is this a noun or a verb? Verb, noun, yes, no. Verb. So when you think of a graph database, all your nouns become nodes, all your verbs become relationships. Okay? Now, this is a simple example that I have. Quickly move forward. Okay. In case of a graph database like Neo4j, you have additional filtering mechanisms given to you. That is what we'll cover. What do you see here? What are the 2 sets of nodes here? Is there a customer node that you see on the left hand side? Yes, no? I know it's difficult after lunch, but I want you to observe as much as possible. So what do you see here? Is this a node? Yes? Yes? People at the back? Yes? This is a node. What is this? A node again. So there is a person node, there is a product node, and there is a relationship. Have you had this encounter that you've bought something from Amazon, you're not happy with the product, so you go online and you give a bad review? This is what has happened here. So customer has bought a product, but he is then rated that product as well. So the relationship, the way you would read this is, a customer has rated a product, that is the relationship. So you've modeled this entire sentence into a simple graph-like structure. Now imagine if there are, so on Amazon, you're not the only one who is reviewing or rating a product, right? There are millions of people who have rated it. But if I want to specifically search for you and my product, what I will do is, I will basically search against these values that you see, right? So there is something called as properties, which are nothing else but key value pairs that help you filter out the right set of nodes and relationships, so that you are able to reach at the right set of nodes and relationships that you are searching for, right? Does this make sense? Yes? So here you have name and email property. So imagine I want to search for the review that Siddhant has given, for example, for MacBook Pro, and I want to ask my database what is the rating that is given. That is something that would be fetched from this particular key value pair, correct? So that is how filtering happens in case of a graph database. Given the advantages of using a graph database, if you want to migrate over from a MySQL database to a graph database, here is a 1:1 mapping. All your rows in a MySQL database become the nodes in a graph. All your joins that you're doing basically become relationships. All your table names become labels. All your columns become properties, the key value pairs that we talked about, correct? So this is a direct 1:1 mapping when you aim to convert your MySQL SQL database to a graph database, okay? Everyone with me? Yes? Perfect. I won't go into Cypher language. So there is a language called as Cypher. For SQL, for writing SQL queries, you had MySQL. For graph databases, there is a language called as Cypher. Again, I wouldn't confuse you a lot. I will move forward to the next part, which is, this is how a graph database looks like. This is basically a movie person data set that I have. How many of you have seen the movie The Matrix? The Matrix, the futuristic movie. So this movie is one node. There are different people who have contributed to the movie. There will be actors who have acted in the movie. There is a director who has directed the movie. There are producers who have produced the movie. All of these linkages is what I have modeled using a graph database. Does this make sense? Yes? Everyone with me? Now, the third section is where I will introduce RAGs. Okay. I work at a bank at this point of time, and I have this very simple question so that every one of you, all of you can kind of get a sense of what RAGs are. Okay. How many of you have bank accounts at this point of time? Digital bank accounts that give you PDF statements of your account statement? All of you? Has it ever happened to you that you want to discover some transactions that you've done and you're too lazy to download the bank statement, and you directly ask this question to Gemini that, hey Gemini, tell me the last major 5 transactions that I've done on Swiggy, for example. Has it ever happened to anyone that Gemini has given you the right set of answers for this query? Any lucky person who has got this answer? Yes, no? No, right? I mean, you would be lucky if your entire transactions have been used by the LLM to train the LLM, but if that hasn't happened, then I'm assuming there wouldn't be anyone in the room who would get answers directly from Gemini. Why did Gemini not answer this query? Can anyone tell me? For all of you use LLMs at this point of time. For a query like a personal context that I have, why wasn't Gemini able to answer this? Doesn't have access to the data. What else? It is trained on mass data. Sorry? So you are saying the training happened long back and it currently does not have that data. What if I ask a question for 3 years back transaction, will it be able to give me the response? No. Then training data in terms of cutoff may not be the right answer. What is correct is the LLM does not have the right context to generate the response.
Sir,
yeah.
LLMs,
yeah.
up to time, I can't train the LLMs.
Yes.
So that is the problem. So we use the prompt for the RAG.
Yes.
RAG what this means, we give the prompt. It search for the internet. It takes for the tools. It validate the LLM is able to validate itself.
Yes.
So it can take over the solvers.
So this is one example of using a RAG application. The other example is, imagine I have a lot of confidential private company data, and if I ask a question on those confidential PDF files, if I don't get a response for that, that is where a RAG application comes in. So if you don't want to search the internet and if you want your private data to be really private and not go to an LLM provider, then that is when you use RAGs. Is this idea clear? A RAG is nothing else but a simplified LLM call with the right prompt and the right context for which you want the answer. Does this add up to what this is? Is there anyone who is still confused with this concept? Yes, no, I heard a yes in between. So typically the idea is for all of the PDF files that you have accumulated over the years, all the document files, all the presentations, PowerPoint presentations, if you want to start asking questions on that, and if you want to keep all of this data confined in a very private environment, that is where RAG applications come into picture. So RAG is retrieval augmented generation. Okay, what does this mean is what we'll cover. This is a typical workflow of how a RAG application is built, right? Imagine I have 1000 PDF documents, okay? Those 1000 PDF documents, what I do is I ingest them into a vector database, right? Now I want to search for a document, I want to search for a small section of the document, which is where rather than passing in individual documents into my vector database, what I do is I break down my documents into multiple subparts called as chunks, right? So imagine I have one entire page. Rather than saving that into a vector, what I do is I break down that entire page into 5 paragraphs, for example, and I pass those individual paragraphs to something called as an embedding model, and that is later on saved into a vector database, right? This is a typical RAG workflow. Now what are embeddings is what you might ask, right? Embeddings are nothing else but vector representations or a list of values defining this piece of text in a higher dimensional space. How many of you worked with Python, Java, C++? Do you remember this concept called as arrays or list in case of Python? Think of embeddings as a list of values. Every row or every element in that array is basically a dimension. When I think of X, do you remember XY plane? XY plane, if I have a vector representing any vector between origin to that point, say 1, 2, then I'll have a vector drawn from origin to 1, 2, right? So in higher dimensional spaces, when I have 300 dimensions, 1000 dimensions, etc., then I make use of this list of values concept so that I'm able to translate a given pair of, say, paragraph into a vector representation or a numeric representation, okay? That is where embeddings come in, and then you save it into an index, okay? Now when a query comes in, right? Now when a query comes in, it firstly goes to the embedding model, it generates a vector representation. This vector representation is searched against this entire index of all the vectors that exist. So it goes through this entire index, it finds out the top k values. So imagine if I have 1 million, say, vectors, and I want to pass the right, say, vectors to the LLM, I will only have 7 or 10 embeddings that I will pass to the LLM. Once that 5-10 right paragraphs are selected from 1 million odd chunks that I have, I will pass it to the LLM and the LLM will generate a response, right? So this is how a typical RAG application works, right? Now I have one question for you, okay? I have 1000 PDF documents and I want you to hear this out very, very clearly, right? I have 1000 PDF documents. Every PDF document contains a biography of a Nobel Prize winner, okay? How many people have won a Nobel Prize from our country? Anyone who can give me the answer without a Google search or a LLM search? Anyone? Can you name any Nobel Prize winner? Rabindranath Tagore, right? So there are multiple people who won the Nobel Prize. Imagine I have 1000 such Nobel Prize winners. All of their biography is captured in one PDF document, which is 1 page only, and I create a RAG application on top of that, right? So what I do is I again follow the same process. I have documents, I have chunks, that is I break down the PDF into multiple sections, create embeddings for every section and store it into an index, right? It works well for most of the queries, right? But when I ask a question like, how many Nobel Prize winners are from United States of America and who have won the award after the age of 40? Do you think this entire RAG application that you've built, will it be able to answer this query? Yes, no? Again, I repeat. Yeah, you're saying something. It will hallucinate, right? The reason is it will not have the right context, because if you see, there is an inherent relationship for which we are asking a query. Our query is, can you give me the count of all the Nobel Prize winners from United States of America and who have won the award after the age of 40, for example. I can keep adding complexity to my query. I can ask how many Nobel Prize winners are from US who have won the award after the age of 40 and who are females as well, right? So I can keep increasing the complexity, and I cannot tell the end user to not give me such complex question, right? So imagine you ask a question to Gemini and Gemini tells me, hey, this is too complex for me to answer, and it doesn't answer, right? So you want the RAG application to be extremely scalable and accurate to a large extent, right? Which is where if you have relationships that you want to answer for, and if your data inherently is not mutually exclusive, that is where you transition over from RAGs to GraphRAGs, okay? So whenever you have a lot of context that you want to preserve, and inherently the context also has relationships between them, that is where you will think of modeling a GraphRAG application and not a typical RAG application. Everyone with me? Yes? Now again, the same piece that I have already covered, but now how does the diagram in terms of creating a GraphRAG system change as compared to creating a normal RAG application, right? So this is something that I have derived from Microsoft's implementation of GraphRAG. There are various other organizations who have jumped in, created multiple implementations of GraphRAG. I will stick to this implementation. There are multiple other implementations as well, but we'll cover this in the short span of time that we have right now, right? So typically you have documents, you create chunks or you break down documents into multiple smaller sections. What you did previously was create embeddings. Here you will create something called as a knowledge graph, right? So a graph that contains all the knowledge from your documents and ingest that into a graph database. So you have entities and relationships or nouns and verbs that you create, push that into a knowledge graph. There is something called as community detection algorithm. How many of you know K-means algorithm? Clustering algorithms, clustering the term. Perfect. If you are there, then you will understand what happens here as well. Then you have graph communities. Then you have community summaries created. And finally, community answers are generated. And then you have the final global answer generated as well. It may look complex, but it's not very complex. Okay. This is the entire stage of what we follows for a typical RAG application as well. You have this entire document, you break it down into smaller sections, chunk 1, chunk 2, this is chunk 1, chunk 2, etc. Now, you will move to entity and relationship creation. If this is the paragraph that I have, I want all of you to pay attention. If this is the paragraph that I have, type 2 diabetes is a chronic condition characterized by high blood sugar levels which can lead to complications, etc. Right? This is the paragraph that I have. I want to create a knowledge graph for it. Is this whatever is mentioned, is it correct? Are these entities or are these nouns? Or is there a verb here somewhere? Are these nouns? Is this correct? Although I've written it and it should be correct, but I want your confirmation as well. Is this correct? These are all nouns that are there, and the relationship or a knowledge graph that you would create would be something like this. So imagine type 2 diabetes is one node and it is linked to other nodes using these set of relationships. This is how you model a typical knowledge graph. You take a sentence, you define the type of relationships that you want to model. Either you will have fixed set of relationships that you want to model based on your RAG application. If you want to keep it free flowing, then you can let the LLM create this entire knowledge graph structure for you as well. So again, the entire control can be given to the LLM to generate this, or you can take control and create this entire structure at your end, right? Now once you have this, it is where the knowledge graph is created, and finally I will come at the hierarchical community detection algorithm, right? So it may get a bit complex, but I'll try to simplify this as much as possible, right? What you are at this point of time is a knowledge graph, right? For the question that I asked, how many Nobel Prize winners are from United States of America and have their age greater than 40, for example, right? Now, one simple question that I have here is, for this set of question, if I create an initial community wherein I define, I have, how much time? 10 minutes, perfect. So imagine if I have, say a community, the way I would define a community is, how do I have a pattern that I kind of discover in this set of nodes. For example, my top level community can be age, my sub community can be gender, my sub community can be, say, country, and the other sub communities that I am able to discover. So you can define communities and sub communities. You can also define at a lower level what the sub communities can be, or let the LLM decide the entire structure for you, right? So if I have a question like, can you tell me all the Nobel Prize winners who are from United States of America? For this question, the LLM or the knowledge graph will be structured in such a way that the top level community will be the country. If I get a result at the top level community, I will pass on that context to the LLM and the LLM will generate a response. If the question is more complex, then it will go inside sub-communities, discover where the result is, try discovering that set of intents, pass that context to the LLM and the LLM will generate a response. How many of you have heard of Hadoop by any chance? Hadoop as a technology. How many of you know MapReduce? This entire algorithm borrows inspiration from MapReduce. So if you remember MapReduce, I'll show you a structure as well. So this is how a Gemini LLM comes into picture. So you can use Gemini to generate entities and relationships. You can have this entire free flow controlled by using an LLM and tell the LLM to generate the right set of entities and relationships and nodes. Once you detect that, you can also tell the LLM to generate relationships at a broader level by generating communities, right? Now, there is one part that I have missed, which is called as community summaries, right? For every community, if I have to discover the right set of answers, I will also have to summarize that community in terms of what this contains. That is where community summaries come into picture. So what you're doing is, yes, communities is a cluster, right? So anything that you think of which is grouped together in a structural form is a cluster. So think of it as a cluster summary or a community summary. You can use the words vice versa. This is how this entire algorithm pans out. Again, in the interest of time, I'll quickly move forward. But for the question that I asked, right, how many Nobel Prize winners are from United States of America, for example, if I want to count, what it will do is, if my first level of community is country, it will get the answer there itself. It will pass on that context in terms of how many nodes are, say, connected to this country query, and it will generate the response, right? This is at a community level. Now, if I ask a question, how many Nobel Prize winners are from United States of America and who have won the award after the age of 40, then it will do a sub-community search, discover where that set of right context lies, and then generate the response. So think of it as a map-reduced kind of structure. So if you've seen this, if you've seen the Hadoop structure, infrastructure, this is how this entire flow happens. Wherever you have the right context based on what you are asking for and where the entire search process lies, all of these right set of sub-communities are selected. That is passed on to the LLM to generate the response, and you get the final response as well, right? Again, something similar to your MapReduce kind of a phenomenon, right? Now, I am not saying that RAGs are bad, but when you have intents and when you want to model relationships, that is where GraphRAGs come into picture. I'll quickly move here. There was this, there's this very famous data set, right? This data set that you see here, right? Where is this? Violent incident news article data set. This is a very unique data set. This data set has never been used in any model training. This is the uniqueness of this entire data set, right? When I take this data set and when I ask a simple question, I create a GraphRAG system and I create a RAG system. When I ask what are the main themes of the data that you have, a RAG output is something like this, which is very simple in terms of the word that it generates, and it's not able to capture the actual themes. Whereas a GraphRAG system gives you this robust, rich answer which captures the relationships as well. So yeah, this is what I wanted to cover. There's something that I have for you. If you enjoyed today's graph session and if you want to keep exploring graphs, you can scan that QR code, learn more about graphs. If you pass an exam, you will get a t-shirt. So this is how the t-shirt appears. So you can basically sign up. Again, you don't have to pay any money to even take the exam as well. All of this is entirely free. If you clear the exam, you will get the t-shirt. If you don't clear, you can retry, and again, you can keep trying till the time you clear the exam. So this is something that I wanted to share. If you are interested in graphs, GraphRAGs and the other things, there's a yearly there's this conference that happens by Neo4j called as Nodes. So you can sign up here. It's scheduled to happen this week itself. So you can sign up, learn more from Nodes as well. And yeah, that's it. That's all that I wanted to cover. Thank you.
So if you want to do Q&A, you can.
We have time?
We are having 5 more minutes.
5 minutes? Oh, I can use this? Perfect.
So if you need to go down, so you
No,
can.
no, I'm comfortable here.
Yeah, sure. So if you
I have 5 minutes with me, which is where if you have any questions, happy to answer those questions. Just 5 minutes is what I have, so yeah.
Good afternoon, sir. Sir, great session.
Thank you.
Sir, if the knowledge base is not saturated and we have more incoming knowledge, but how can we implement that in this so that the information that's given by the RAG is accurate?
So I got the question. So imagine if the knowledge base is not static, it constantly updates day on day or month on month. How do I manage this entire knowledge base? Good question. I think I cover the advantages of GraphRAGs, but one thing that I don't mention is I wouldn't say it's a pain, but it's very difficult to maintain a GraphRAG system, because when a new data comes in, you will have new relationships. So you'll have to wipe out relationships that are not relevant, and then you'll have to append new relationships which are say relevant. So if you have to manage a GraphRAG system, you will need people to actively manage the GraphRAG system, and that is how you can achieve scale. There is always a trade-off that you make, because essentially by using GraphRAG, if your accuracy increases from 90 to 99%, I am okay to have a couple of people managing the entire graph database for me. So yeah, it's a challenge to manage a GraphRAG system. That is for sure. Yeah. Yeah.
Hi.
Yeah. Hi.
What about the redundancy factor, which happen in every database?
So in case of a GraphRAG, given that you're modeling nodes and relationships, your redundancies will be captured in the same set of nodes and relationships. If you have by any chance still created redundancies by mentioning the same node names again and the same relationships, you can remove that using a code as well. So you can write cipher queries to remove redundant nodes and relationships and remove that data that exists. So you can gracefully manage redundancies in case of a GraphRAG system.
Sir, thank you, sir.
Yeah.
One more question. If RAG cannot hold multiple elements, how do we solve it?
No, can you repeat the question?
We have LLM, right?
Yes.
We can connect the agents, AI agents. We can connect with the RAG also.
Yes.
RAG also.
Yes.
If LLMs cannot handle means some agents, we cannot RAG.
Okay.
And if RAG cannot handle the problems, how do we solve it?
Typically, you can always have a fallback mechanism for any RAG application. If you're not getting the right set of context, then the LLM will give out a default response. If you have the right set of context, then your GraphRAG or a normal RAG can also basically handle this, right? For a fallback situation, you can tell the LLM to handle it gracefully. So irrespective of whatever you use, you can basically gracefully handle the situation as well.
Basically, fine tune the LLM.
Yes, you can do that as well.
Thank you, sir.
We have.
Thank you for the wonderful session.
Thank you so much. Yeah.
And see, the data get stale after some time. The fact today cannot be true tomorrow.
Absolutely.
So how are you going to manage that?
So there is something called as, there's a library called Graphity, which manages all of this very gracefully. So there is something called as a snapshot that you take for a graph database at one point of time, and once you ingest new data, once you remove old data, you can move on to the next snapshot as well. So all of this, there's a library that is built on top of Neo4j or graph databases called Graphity. You can use that for this entire situation. Yes.
Thank you for the nice
Yeah.
presentation.
Thank you.
Presently, we are only using like NoSQL databases like MongoDB and so on. So, is it you think it's a good idea to convert like all NoSQL databases to GraphQL databases? And maybe I can also answer the second part of the question related to an application. Like say you are collecting sentiments of from various YouTube channels for say use case of product reviews. You are handling tech product reviews and you simply collect sentiments for laptops or mobile phones. So you store the sentiment data in a NoSQL database typically. Can you explain the use case for this kind of situation? Like a two-part question.
One question that I have is, are these channels interrelated by any chance, or are they mutually exclusive?
They have a common interrelation because they're talking about the same product. Like say a MacBook release or
Yes.
a new iPhone release. You
Yes.
are
Then, yes, as soon as a bit of exclusivity comes in, wherein you have some amount of relationships between individual entities that you're capturing, then there is merit in moving towards a graph-based system as compared to a typical, say, NoSQL database. All of this again boils down to what you're trying to solve for at the end use case as well. If there are queries that you want to run, wherein you want to ask complex queries across applications which have, say for example, MacBook reviews, right? If I ask a simple question, which user has given the maximum, say positive rating for MacBooks, for example, out of all the YouTube videos that you've scraped, then to filter all of this, a typical RAG will not work. A typical, say, if you want to do a simple search, then Elastic or MongoDB will give you the results. But if you want to perform analysis on top of this entire system on the relationships, then a GraphRAG makes a lot of sense. So it's a application specific use case, which is where you will have to design for. So for this application, if you get a lot of queries where the end application is based on relationships, then it's good to move away from say NoSQL to Graph. If not, then there is merit in sticking to Graph itself, NoSQL itself.
Basically, you have to think in your head what are the entity relationships that I can create for this data.
Yes, and what the end users will end up asking and consuming the solution as well. That is where you will kind of get a answer in terms of whether you should transition from NoSQL to Graph.
Thank you.
Cool. That's all the questions that we had. Cool. Thank you so much, everyone.
Thank you, Bhavesh. To acknowledge the valuable insight shared by Mr. Bhavesh Bhatt in his session, we are pleased to present him with a memento. I request Mr. Raj Kishore to kindly come forward and do the honors.
Thank you so much. Thank you so much. Thank you. Perfect.